How's everybody doing today? Welcome back to the Math 140 lecture series here, Math for Healthcare. Today we're going to start talking about linear regression and really the idea of linear regression, and we'll learn more about how to use it and do some examples in the next lecture. Now, what linear regression is basically it's a idea that maybe we have some data that's not really, they don't all land on a line, okay? But we could estimate what a line pretty well. Sometimes we can, sometimes we can't. And part of using linear regression is understanding when it's good and when it's not. So, and this is, I should say, is this technique of linear regression is used all the time. And it's really the basics of what modern machine learning and artificial intelligence is based on. All right. Yeah, things have gotten way more advanced, but this is the original sort of idea of, okay, we want to find an answer to something. What's the best answer according to some data? And that's really what is going on in modern machine learning classes. Okay. So anyway, for us, it's above and beyond. It's a useful tool. So we're gonna go through it. So let's see an example where it may come up. Is remember last time we had a hospital that purchased a machine for $225,000. They estimated each MRI would cost the hospital $750, and they decided to charge $2,000 for each MRI. They need to give 180 MRIs to pay for the machine. Right, that's what we found last time. One thing I want to note here is, just as a little bit of a review, we got our MRI machine. Remember we said, okay, so the cost function is like that's 750 per MRI. So the units on that are dollars per MRI, and that tells us it's the slope of our line, of our linear function, plus the fixed cost, 225,000, and that's in dollars, okay? And X is in items, or number of MRIs. And then similarly, the revenue function, let's see, 2,000 per MRI. Again, that tells $2,000 per MRI. That tells us that that's our slope, because it's the units of the Y over the units of the X, and that's times X. Okay. Now, problem is, after a year of operation, the CFO, the hospital, begins to suspect that the hospital underestimated the cost of administering MRIs. So, she's wondering what to do. And what she did is, for each week in the previous year, the CFO gathered the number of MRIs given in a week and the cost of operating the machine for a week. All right. And this is what that data looked like. And by the way, this says, okay, 5 MRIs per week was somewhere about, so 5 MRIs per week was somewhere about, or no, I'm going to guess about $3,000 that week. There may be other weeks. Look over here, we could see that it's not really a constant. If we look at these data points that are all, okay, those were all weeks that had about 7 MRIs or 6 MRIs, and look how much the cost ranged from somewhere about 4,000 up to somewhere about 8,000. All right, so we want to look at this and use the power of linear regression to get, even though these things don't fit on a line, there's certainly something linear about looking at this scatter plot. And scatter plots are important to look at before we just go in plugging numbers in. And the idea is linear regression is going to help us find this line here. Obviously, that's approximation. I'm just drawing in. but we want to know, well, what's the one that fits the data the best? Okay. And we'll use that to estimate the cost function. Right? So these are a lot of data points. Let's look at linear regression specifically and what it does in order to find that best fit line. All right. And when we're looking at that data, right, there was a fairly clear positive linear relationship. Positive, right? The line has a positive slope, and it's fairly linear in shape. It's quite linear, actually. There are many possible lines in linear equations that model the situation, so we want to identify the best one, like we were saying. So we need to be careful about what we mean when we say best. So I want you to think about maybe what would the best be. Turns out the best is to minimize the error in our estimation. In other words, find a line simultaneously closest to all the points. And, you could see by hand, I drew in something that's reasonably, I'm not saying that's the best fit line, but it tells us that's what we're trying all lines that are going to be similar to that, and we want to find the best one. All right, now let's think about how to do that. Let's consider a small example now, something that we could parse out in this beginning of our venture into linear regression, which is, again, I want to remind you, it's a powerful tool. So this is a good one. So now we're considering these points. So let's say we had some data points 1, 2, 3, 2, 4, 4, 5, 6, which, by the way, I have down in my lower left Desmo screen there, plotted. And we want to look at and that's the blue points. There's a blue point here, blue point. The one red and blue is sitting on the line. Okay, because we look at it, the data's blue. This is red and blue right there, red and blue. The data's in the blue, the actual, and then we have our estimate. Here, we drew in the line. If you could see it, maybe try and guess what it is, but notice where it goes through. We tried the line y equal to x, and by the way, similarly, that line is graphed down in my lower left screen there through, and it goes through this, data point 4, 4. How does that fit? Okay. It looks like it's pretty close, no? But what does it mean? How do we test it? What does it mean? How do we know how bad it is or how good it is? Well, we use this estimation error, which kind of makes sense. So we have this is, for this first data point, this is the actual in blue, the actual. And the red is the predicted by our line, right? I plug in 1 for x, I should get 1 for y. That's what my guess says. And, well, what are we interested in is, well, certainly the 2 minus the 1, that length of that red line, right? Notice that length of that red line there is 2 minus 1, or 1. And that's what we call the error of that point. And we'll call that E1 here because that's the first data point. Similarly, we have this guy and this guy, right? And their error, there's 0 error. E3 would equal 0 in this case. Now notice this error here, the second one, going back a little bit, this error, E2, would be a negative number compared to the other one. Okay, so and that's what, there. -1, I believe. -1. Okay, that's just a note, and that's the idea. I think that makes sense for the error, and finding each one of those EIs. In this case, there's 4 of them, right? So, what? Maybe that makes us think what we should do is look at the sum of the errors. Okay, again here. We have error of 1, error of -1, 0, and 1. All right. Now, why don't we want to just sum up those errors? We've got to be a little careful. What happens if we sum up these errors to get an idea? 1 plus -1 plus 1, that just equals 1. These two cancel each other out, so we don't want to deal with the negative signs, right? We don't want error. That negative tells us what direction it is, but we don't really want to do that when we're thinking about it being an error. Those should add together, not cancel each other out. Okay. So instead, we square the error. We square the error. All right. Obviously, this will give us a positive value, which is nice. Why don't we use absolute value? Because it's kind of a pain to deal with mathematically. It's not quite as nice as squared. All right. And so we're using the square error because we want to penalize large errors more than small errors, and that square is doing that, right? The difference between E1, let's say E1, the bigger it is when you square it, the more it exaggerates it, right? And then there's a little bit of a technical math reason, which I was saying is that absolute value is kind of a little bit of a pain to deal with when it comes to these sorts of things. Now, luckily, this is something in math we're always interested in. Is there a unique line that fits this best? And there is, and we call that line the least squares line, the line of best fit, or the regression line. There are formulas for the slope and the y-intercept of the least squares line, and it'll probably show up in your textbook, but we will always use technology to calculate the linear regression line or the least squares line. That's important. You'll spend way too much time adding things together and doing it by hand. Okay? Now, here's quick. How do we do it on a TI calculator? Because in the next video, I will do it in Desmos, and we will. You'll see how to do it there. But first thing is, only once, is we want to get the diagnostics on. In order to do that, you press second, then 0, scroll, and select the diagnostic on. This will display the correlation coefficient, which we'll define later, but this basically tells you how good your fit is. Now to enter the data, press stat, then edit. L1, L2 represent X and Y respectively. In other words, your X values go under L1, your Y values go under in the list 2. And to calculate the squares line, once your data is entered, press stat, then scroll over to calc, and then scroll down to linreg, and press enter. By the way, as you should also look at the scatter plot of your list 1, list 2 before you do the regression analysis or get the regression line to have an idea whether it's linear or not. All right. So here, and that's why I find Desmos to be a much nicer spot to do regression. Not only can you see the scatter plot much more easily, but you also have the capability to cut and paste tables of data from some kind of Google Sheet or Excel file, either or you could. And that's a big benefit to me, not having to do it all by hand. You can do bigger data sets and such, right? But you could get by in this class with you doing it on a TI calculator, but I do not recommend it. I recommend using Desmos for your regression. All right. And so next time, just a little preview here. Maybe we should finish up with this actually. The minimal example revisited. When I turn, let's see here, what happens? Looks like we get our regression line is y hat equal to, by y hat we use y hat to mean predicted, right? Because we know it's not right. It's an estimate or estimated value or estimated. Okay, and notice here we get it's slightly different than the line that we got. And I guess I'll plug this in quickly in that lower left corner. What you do is you say, I want my estimate to, and by estimate you use y1. Notice that's what's in my Desmos area here. And then you use tilde to say estimate instead of equals. Okay, you want to estimate the y values with your x values, and here you could use m times x1 because that's your list there. And this is if it's going through the origin, but we want to be able to go through anything. And there our numbers come up and our lines plotted. Notice it's slightly different, and it is of course we get this line y hat equal to 0.971 times x plus 0.343. And you see that is slightly different, and it turns out that it is slightly better than the other line. All right, again, here's another picture of the side-by-side comparison up front, and we see that the error for y equal to x is 3. The sum of the squared errors is 3, whereas the sum of the squared errors for the least squares line is 2.74. Okay, so a slightly better fit. All right. Well, hopefully you enjoyed that. We'll see more how to use this in the next video, and we'll probably have one more linear regression video after that that goes over the correlation coefficient and thinking about fit. All right. Have a great day, and I'll see you in the next video.